Hello everyone, I welcome you all to the course of heat transfer. Today we will discuss a couple of problems on convection. The first problem is like this. Air at 20 degrees Celsius at atmospheric pressure flows over a flat plate at a velocity of 3 meters per second. If the plate is 1 meter wide and 80 degrees Celsius, calculate the following at x equals to 300 mm. First one is hydrodynamic boundary layer thickness, followed by thermal boundary layer thickness. Next, local friction coefficient, then average friction coefficient, local heat transfer coefficient, average heat transfer coefficient, and the last one is heat transfer. Now, such problems generally will be asked in your examination, wherein you need to write down the formula related to each parameter and you need to calculate for a given case. Now, if you understand the problem, you have a plate which is 1 meter wide and the length is not given, but you need to calculate all the parameters at length x equals to 0.3 meters or 300 mm. And the plate is at 80 degrees Celsius. Over this, air is flowing with a velocity of 3 meters per second and the temperature of air is 20 degrees Celsius. So this is the problem given. Now before we begin the solution, first we need to calculate the film temperature. As we discussed already, film temperature is nothing but the average temperature of surface as well as fluid. The fluid temperature is 20 degrees Celsius and the surface temperature is 80 degrees Celsius. The average temperature is 50 degrees Celsius. Now you need to calculate or you need to note down the properties of the fluid at film temperature. We have calculated the film temperature as 50 degrees Celsius. As the flowing fluid is air, you need to take the values of air at 50 degrees Celsius. Now, using your data handbook, one can get the property values. Now, referring to the 8th edition of Heat and Mass Transfer Data Handbook, on page number 34, you have property values of gases at 1 atmospheric pressure. The first fluid itself is dry air. If you see the table, you have the properties of air from minus 50 degrees Celsius to 1200 degrees Celsius. Now we need to get the value corresponding to 50 degrees Celsius. Now for 50 degrees Celsius, you have the first column density, which is 1.093 kg per meter cube. Next is absolute viscosity or dynamic viscosity, which is 19.61 into 10 raised to minus 6 Pascal second. Next is kinematic viscosity, 17.95 into 10 raised to minus 6 meter square per second. Next we have thermal diffusivity. Prandtl number we can have, which is 0.698. Specific heat is 1005 joules per kg Kelvin, or it could be 1.005 kilojoules per kg Kelvin. Then thermal conductivity 0.02826 watt per meter Kelvin, or 28.26 into 10 to the power minus 3 watt per meter Kelvin. So we can avail these property values from the data handbook. Next, we need to know whether it is laminar flow or turbulent flow. Now, once we conclude that it is laminar flow, we should use the equations corresponding to laminar flow. Else, we need to use the equations corresponding to turbulent flow. That is judged by a non-dimensional number called as Reynolds number, which is given by VL upon mu, or rho VL upon mu. So in this case, this is kinematic viscosity. If it is rho VL upon mu, that mu is nothing but dynamic viscosity. You can put any of the formula. You will be having the property values for kinematic viscosity as well as dynamic viscosity. Now, where u is nothing but the velocity, L is nothing but the length at which you need to find the boundary layer. So in this case, he has asked us to calculate at x equals to 300 mm, which results into 0.3 meter. And if you substitute the value of kinematic viscosity as 17.95 into 10 raised to minus 6, you will have a Reynolds number as 5.01 into 10 to the power 4, which is less than critical Reynolds number 5 into 10 raised to 5. Now we can say that the flow is laminar. And from the definition or from the description of the problem, one can say that it is an external flow because air is flowing over the plate. Now, corresponding to external flow, we have different equations. That too, for laminar flow, we have different equations, and for turbulent flow, we have different equations. Now we have determined that it is an external flow. At the same time, it is laminar flow. Now if you turn page number 113 from your heat and mass transfer data handbook, you have different equations for hydrodynamic boundary layer thickness, thermal boundary layer thickness, then local friction coefficient, average friction coefficient, all the expressions you can have in the data handbook. Now the hydrodynamic boundary layer thickness, it is given as 5x into Re to the power minus 0.5, where x is nothing but the distance where you need to calculate the boundary layer thickness. Now, from the problem statement, it is clear that we need to calculate the boundary layer thickness corresponding to the value of x, which is 300 mm or 0.2 meters. Now, if you substitute the value of Reynolds number that you have obtained, you will have boundary layer thickness as 6.7 into 10 raised to minus 3 meter or 6.7 mm. Next is thermal boundary layer thickness, which is given next to the hydrodynamic boundary layer thickness. We have discussed already, Prandtl number is a function of hydrodynamic boundary layer thickness and thermal boundary layer thickness, or Prandtl number is the ratio of hydrodynamic boundary layer thickness to thermal boundary layer thickness. It could be for varying for different materials. Now, if you substitute the value of Prandtl number, which you have extracted from the data handbook, you will have thermal boundary layer thickness as 7.5 into 10 raised to minus 3 meters. So you substitute the value of hydrodynamic boundary layer thickness, which is 6.7 mm, and Prandtl number. Next is local friction coefficient. Again, that is given in page number 113 of 8th edition. That is given by CFX is equals to 0.664 into RE to the power minus 0.5. Now here again you need to use the Reynolds number that you have calculated. If you substitute the values, you will have local friction coefficient as 2.96 into 10 raised to minus. It is also given by a formula shear stress upon rho v square by 2, which you can find in the column of rotations. Sometimes that will be used in order to calculate the shear stress. Next is average friction coefficient, which is 1.328 into RE to the power minus 0.5. If you calculate the value, you'll have average friction coefficient as 5.9 into 10 raised to minus. The next bit of the question is you need to calculate the local heat transfer coefficient. In order to calculate, you need to use the equation for local Nusselt number, which is given by NEX is equals to 0.332 RE to the power 0.5 into Prandtl number to the power 0.333 or 1 upon 3. That you can find in equation 1.1 in page number 113. If you substitute the value of Reynolds number as well as Prandtl number, you will get local Nusselt number. Once you equate that local Nusselt number with HL upon K, you can have the local heat transfer coefficient. Now, if you substitute the value of Reynolds number as well as Prandtl number, you will have Nusselt number as 65.9, and if you equate it to H into L upon K, where K is obtained from table. In this case, K is nothing but the thermal conductivity of the fluid. In case of Biot number also, you will come across HL upon K. In that case, K is the thermal conductivity of the solid material. While defining Nusselt number, the K is with respect to the fluid. This change you should identify. Now once you put the values of L and K, you will have local heat transfer coefficient as 6.2 watt per meter square Kelvin. The next bit of the question is we need to calculate average heat transfer coefficient, which is 2 times the local heat transfer coefficient. Hence, you will end up with a value of 12.4 watt per meter square Kelvin. The last bit of the question is we need to calculate heat transfer, which is given by Newton's law of cooling, that is HA into delta T. In this case, you should use the average heat transfer coefficient. And area, as we have seen, it is nothing but a rectangle with a width of 1 meter, and we have considered the length to be 0.3. If we consider that as the area of a rectangle is width into length, which is 1 into 0.3, and the change in temperature is 60 degrees. You will have heat transfer as 23.3 watts. Moving to the next problem. Air at 40 degrees Celsius is flowing over a flat plate of 0.9 meter at a velocity of 3 meter per second. You need to calculate overall drag coefficient, average shear stress, compare the average shear stress with local shear stress. Again, the fluid is being air. You need to get the values of air at 40 degrees Celsius. Now, the properties of air at 40 degrees Celsius, if you consider density, it is 1.128 kg per meter cube. Kinematic viscosity 16.96 into 10 raised to minus 6 meter square per second. Prandtl number 0.699. Thermal conductivity 26.56 into 10 raised to minus 3 watt per meter Kelvin. So these properties can be obtained from heat transfer data handbook, which is in page number 34. Under the property values for gases at 1 atmospheric pressure. Again, first we need to know whether the flow is turbulent or laminar, which will be determined by Reynolds number. The velocity is given and the length of the plate is 0.9 meter. And if you substitute the value of kinematic viscosity, you will have Reynolds number as 1.59 into 10 raised to 5, which is less than the critical Reynolds number. Now please understand, this problem is also over a plate, hence the critical Reynolds number is considered to be 5 into 10 raised to 5. If it is tube and internal flow, the critical Reynolds number is 2300. If it is open channel, the critical Reynolds number is 500. We have discussed earlier. Reynolds number varies for different passages. It need not be same for all. Now, for laminar flow, the drag coefficient or average skin friction coefficient is given by 1.328 into Re to the power minus 0.5. You will have the average friction coefficient as 3.3 into 10 raised to minus 3. Now we know that the drag friction coefficient is shear stress upon rho v square by 2, which is given in the notation part of local friction coefficient. Now if you use the formula, you can get the value of shear stress tau. This is average shear stress, which is 0.016 Newton per meter square. Now if we want to calculate the local skin friction coefficient, it is given by 0.664 Re to the power 0.5 with a negative sign. If you substitute the values, you will have local skin friction coefficient as 1.66 into 10 raised to minus 3. Now if you use the same equation of Cfx is equals to shear stress upon rho v square upon 2. Now as we have substituted the value of local skin friction coefficient, we will be getting the shear stress corresponding to that position, which is a local shear stress. Now if you substitute the value of Cfx as 1.66 into 10 raised to minus 3 and the value of density as 1.128, velocity to be 3, we'll have the local shear stress as 8.4 into 10 raised to minus 3 Newton per meter square, or 8.4 into 10 raised to minus 3 Pascal. Now in the question he has asked, we need to compare the local shear stress with average shear stress. The local shear stress is smaller compared to the average shear stress, and if you take the value or the ratio of these two, you will have a value of 0.5. It means the local shear stress is half of the average shear stress. With this, I will stop here. Thank you.